Is this visible?
Yes, ma'am, it's visible.
Isn't okay. So shall I start?
Ma'am,
Can you hear? Yeah, can you hear
ma'am,
me
your video
properly?
is not coming.
Oh,
Ma'am, your
but
camera is
it's
switched off.
okay. Maybe here is just 1 minute. Is this now on?
Yes, ma'am. Thank you, ma'am. You can
Oh,
start.
oh, oh, yeah. Just a minute. So first of all, thank you for inviting me and giving me the opportunity to speak in this uh, like new and like new the recent trends on or the whatever the topics are covered in this 5 days short-term course. And secondly, I have seen those topics are they are interrelated but not totally overlapped. So as per my knowledge, looking at the topics in last 1 day and today first half, what are the things covered, they are mostly on the converter, microgrids, and those aspects, and not properly on battery or sizing. So if I'm like remembering correctly, the previous lecture was on mainly on converters, focusing on converters for microgrid. So in all these cases, probably just one thing, if you ever like find my audio is not properly coming, just let me know. So as I was saying, these are very interrelated. So
Sorry,
you
sorry to
probably
interrupt. Sorry to interrupt, ma'am.
yeah
Can you please
yeah
full screen your slide?
sure. Actually, I haven't started, so that's why. And now it's okay.
Yes, ma'am.
Yeah. So basically, in those cases, you have seen that battery are like kind of essential part of those systems, and whatever you see that uh, these days probably in the bigger applications or smaller applications, the energy storage is an important thing, or you can say unseparable. So in that sense, this topic I think is of interest. I'm not sure the audience or the participants who are listening to this lecture whether they are like fully aware of this topic, or some of you maybe like may know better than me what I'll be talking about. Some of you may not know at all this topic, and some of you may have some idea. So definitely I can't cover, I mean, take care of this full range, like who like totally unaware and fully aware, and as I said, that know more than me, or so I will try to think in this way that there are some participants who would like to probably um, uh, gain the knowledge, like in which area, or they are searching for some new area to work on. So of course this would be of interest to them. And the second thing, who are working in this area, they may get a new aspect, because the work I'll be presenting is one of my students' work, Sakshi Bansal, who is presently doing postdoc in Singapore Institute of Technology. So most of the work I'll be presenting is her credit. She defended her thesis recently, so this work is not very old, but of course not very new too. So keeping that in mind, if you at any point of time you have question, you can ask me. I can't like ensure that I'll be able to answer all the questions, but I will try my best because this is our work. So whatever I know, I will tell. And if I can't answer at this moment, I will take up that question, and I will get back to you later on if I can find the answer. So with that one, so today's topic is, this session's topic is sizing of energy storage systems in electric vehicles. So what I'll be talking about, first a small introduction where I'll talk about this sizing and electric vehicles, so kind of motivation, Some of you may feel bored with this one because this is not very new. And the second thing, I'll be talking about what optimal sizing is, and then like that we will apply on a particular case. In our case, it's one case is e-rickshaw, and the second thing we'll be talking about some practical issues which most of the times we ignore when we do the laboratory based work, and that is the uncertainty. And in that case we will consider a city bus, and then third, if time permits, I will move on to as the machine learning is these days is being explored or exploited in every field because it has potential to do some good, and especially to save time and improve accuracy. So we will also talk about if conventional optimization, instead of that, if we move to the machine learning based algorithm, then like what facilities we may get, or advantages and disadvantages both, of course, if time permits. So I have kept that also, but I'm not sure if I'll be able to cover. And then some discussions on what, if anyone wants to work in this field, then what area are open, I mean, they can directly take up. And finally, so here the first of all, as my topic is also not only battery but on the electric vehicle mainly I'm talking about. So here I would like to point out, let me take the pointers. So here the contribution of transport sector, because we are talking about the electric vehicle. So the left one is what are the contributors. So air pollutants coming from this NOx, OX, then this CO and HC, all these things are there. All of us know. And this is a 2019 study. And then the second part is specifically that which sector is contributing to what. So if you see, the transport sector is 25%, and that to the studies of 2021. So if we look at 2023, probably I couldn't find it ready-made. So if we look at 2023, probably it will increase. So as and we know that the government of India is also targeting for all EV, if not like in 2030, but in 2050. And so we have targets. And why the target is because of this thing, that this transport sector is contributing to the pollution a lot. And now, so what is the solution? Now we are moving to the electric vehicle from the internal combustion engine or IC engine vehicle. Now, if we look at the IC engine vehicle has many advantages also, but the main problem here, huge tailpipe emissions. And whereas in electric vehicle, ideally zero tailpipe emission. But in this case, when we talk about zero tailpipe emission, we are assuming many things, that the battery is getting charged from the grid, which is also green. So based on all those assumptions, which we can think of that in future will be taken care of, with that condition being fulfilled, we can tell that electric vehicle is the zero tailpipe emission. So this is the main advantage. Another one is it's of course quieter than the IC engine vehicle. Its efficiency higher because the less moving parts. So maintenance also comparatively better scenario. But the main issues are limited range. At this moment, why people are not going into the electric vehicle is limited range, high initial cost, and less charging stations. Specifically, if we think of India, of course, less charging stations. You won't find probably these days as Chandigarh highway, they have a lot. But if you think overall India, this is very less. And in coming years, we can expect a lot. So these three things are where actually IC engine vehicle are advantageous. So if you map these three things, limited range is because of what? Because of the fuel. And in case of EV, fuel is the battery or energy storage. That can be something other than battery also. Mainly three things are used. One is battery, one is fuel cell, another one is the supercapacitor or ultra capacitor. So these three things we hear like when we talk about the storage, I'm talking about battery. Like when I say battery, I'm not meaning only battery, similar energy storage. So if you map this Am I audible and visible now?
Yes, ma'am.
Okay. I'm sorry, it got disconnected. I don't know why. So let me make this. Okay. So what I was telling that these
Sorry to
three
interrupt, ma'am.
things. Yes,
Ma'am, your
please.
slide is not visible. Ma'am, again you have to share the slides.
I think so. Thank you. Thank you for pointing this out. Is this okay?
Yes, ma'am. Just full screen.
Yeah. Yeah, sure.
Thank you.
Okay. So what I was telling that these 3 points, limited range, high initial cost, and less charging stations, they all are related to the energy storage only. Because if we go for low capacity, you can think of fuel tank, in this case, low capacity battery or energy storage, then we can't move like high range or we would say key for a big journey. And then second thing, if we go for high capacity, then it will lead to high cost. And these two things, there can be, it is possible that with the low capacity we can travel longer, provided there is refilling option. So it's you can I mean have like analogy with, you have a 500 ml water bottle and you can have 5-liter water bottle. So when, which one is possible to take? If we have the refilling option, then we will take 500 ml and multiple times we will refill, but totally we can get 5 liters. But if we do not have, then we have to carry a maybe 5-liter or more depending on our requirement. So all these things basically are telling that we need a proper or appropriate capacity energy storage device. So now how to get rid of that, and what kind of problem it can create if we do not choose an appropriate energy storage. So firstly here, when we talk about sizing, because the topic, the title of this discussion or topic is sizing of energy storage system in electric vehicle. So what the sizing is, who are new to this, they may think of, when we talk about size, it's physical size, but in this case it's not the physical size, but it is the electrical capacity. So that means in ampere hour we can think of, so voltage, current, ampere hour. So typically in case of battery we think in terms of ampere hour. In case of supercapacitor, we think in terms of how much farad, but along with that, we also talk about the current and voltage because they are interrelated. So basically, the size of ESS in EV, not only in EV and anywhere, when we talk about size of ESS, so it refers to its electrical capacity. Yes, physical size is also involved while finding out the optimal capacity, but our focus is mainly on the electrical capacity when here we talk about the sizing or size. Now in case of EV, so here basically sizing means to choose the electrical capacity which will be able to satisfy the drivability requirement of vehicle, but at the same time we need to think of the safe operation, because many of you have seen that these days so many accidents are happening. Some electric scooters go down. Even there was fire a few months back in South India, in Delhi, and in many places of India, we can see the fires are there. So safe operation is also important. So number one, it must fulfill the drivability requirement. That means you want to travel from one place to another, it will be able to take you there. At the same time, you want a particular speed, so it would be able to run the vehicle in that speed, acceleration, and all these things. Because you have seen probably the IC engine based auto rickshaw and the battery based e-rickshaw, you will find the speed of the e-rickshaw is lesser than the normal conventional old day auto rickshaw. So why? Because of this thing that they have a speed limit due to the battery involved in this e-rickshaw. Same thing in car also. You may need you want higher speed probably, but depending on the, so manufacturer here, they basically tells you or limits you to a particular thing. So many things are involved. Um, so everything to be fulfilled as the manufacturer is saying. At the same time, safe operation is of course one of the important thing, or rather I would say the same importance as the drivability requirement, if not more. So total capacity, how we decide? Now that is depending on the total number of cells used. Now when we talk about a battery, is it a single battery cell? No. Most of the times when we talk about battery, it actually in three terminologies are involved. One is called battery cell, second is battery module, and third is battery pack. So the highest level we talk about is the battery pack. Within a battery pack, there can be multiple modules, and within a module, there can be multiple cells. And how those cells are connected? They may be connected in series and parallel combination, as shown in this diagram. Yeah. So you can see here this nbat underscore p and nbat underscore s. What does this mean? That how many cells are connected in series, or battery cells are connected in series. So here 1, 2, suppose like here multiple 6 more. So total 10 cells are connected in series. And here suppose another 2. So 1, 2, 3, 4, 5, 6 such series branches are connected in parallel. So in one series branch, we have, for example, if we consider that 6 cells, and in parallel such 6 series branches are connected. So 6 into 6, total 36 cells are there. So each cell has a capacity. So then 36 into that capacity would be the total capacity of this particular battery. Now, is it always the cells will be connected in this series parallel combination? No, they can be, there are probably battery where only series cells are connected. So as we know that when the cells are connected in series, we are increasing the voltage, and requirement of the current is high, we will connect them in the parallel. So depending on our requirement or depending on the requirement of the vehicle, the battery packs are made in that way. So here, when we talk about sizing, basically we want to find out the total electrical capacity, and how that is found out. Now, it may happen that suppose, as I said, 36 cells will be able to satisfy one drivability like requirement, power requirement. Now 36 can be connected in many ways: 12 into 3, 6 into 6, then 18 into 2. How we will connect them so that my purpose is fulfilled and the cost is minimized, that is what basically our objective. So finding out the number of cells in series in a branch and how many such branches to be connected in parallel, that is what we are talking about here. So what are the here like the factors which basically have led to this optimal sizing thing? So optimal thing, we know that it's not the best choice, but when we talk about optimal, when we have the multiple things, then based of those options, it's not the best of each, but based of the combination. So here, when we talk about optimal sizing also, we are satisfying multiple things, and then we are calling it the best. So why we need the optimal sizing of energy storage? The number one, to protect the energy storage device from overcharging and undercharging. That means what? If you use a low capacity battery and you want to run longer, then what will happen? It has to discharge very low, and that may not be very healthy for that particular device. And again, it may happen that you need to charge it to the 100% when it is not recommended, because you want to go up to a particular range. So that is one thing. Secondly, when we are talking about optimal, as I said, it is the based of considering all the factors. So to properly utilize one thing, if you use very high capacity, that means underutilization. If you are using low capacity, or range anxiety will be there. So to take care of these things, then optimal sizing is important, which will take care of all these factors. Then if you go for high capacity to get rid of range anxiety, your cost will go high. So that also be taken care here. It will save your battery life if you choose a proper size. Now, there are many such things which like this optimal sizing will take care. So what is the present status? How the things done presently? So one thing is conventional method. This is early days, not at this moment. The situation is moving from the experience based to the technique as well as the experience, both the things. So in early days, what used to happen, that is based on the mainly on experience, and it's not a very detailed calculation. We know, okay, this voltage requirement, this is the current requirement, and so let us go for this one. What usually used to use in the e-rickshaw when it came in the beginning, that lead acid battery of this voltage. uh, so what is the advantage of this conventional method? The advantage is that it is simple and fast. And what are the disadvantages? Of course, as we said, it may go over capacity or under capacity. And in both ways, we never want actually to be under capacity, because then in the middle of your journey, you may need to stop. So most of the times we provide the higher capacity. So that's why the initial cost comes to be higher, and people are not, that's why, like going for EV more. Of course, charging station is one important thing, but this is also another factor, that initial cost is high. And if we look at the optimization method, which is the present scenario, because it is moving, the industry is moving towards this. And as I said that they are moving towards machine learning too. So here advantage is it provides cost effective. That means it considers many factors which manually we can't consider. So you write a program where you feed all the factors which you want to take care, and then you want the best of that, those like combining them. And the disadvantages, of course, computationally complex. So what are the factors which affect sizing? Number one, of course, what kind of energy storage device you are using. As I said that in this specific like topic we are talking about, the three things which are called electrochemical energy storage also, so that is battery, fuel cell, and supercapacitor, which is also called ultracapacitor. So depending on which type of things you are using, that will affect your sizing, because battery and supercapacitors, they are of high energy density, whereas battery and fuel cell, whereas supercapacitor is of high power density. Of course, depending on your choice, your sizing be different. Then the topology. The topology means how the components in the powertrains are connected. So whether your battery is directly connected with the DC bus, or the converter is in between, like whether you are using only one type of storage, for example, only battery, or only a supercapacitor, only fuel cell, or you are combining one of these and on, which is called hybrid. So single or hybrid. And when you are using, so the single or hybrid, whether you are going for the fully passive, fully active, semi-active, all those things, they are also uh, will affect. And driving patterns, of course, this is an important factor. Model of EST, I will at this moment not consider. Vehicle dynamics, of course, vehicle dynamics is an important factor, because like in some vehicles, your mileage is 10 kilometer per liter of petrol, for example, and in some vehicles it's 20 kilometer per, the same 1 liter petrol is running it. Why? No, because there are it's not only the vehicle dynamics, it's along with that other requirement which are in that particular vehicle. So when I'm talking about vehicle dynamics, because the structure of the vehicle, many other things are involved, we will see that how the vehicle dynamics is part of the sizing. Then temperature and aging characteristics, the same battery, like how it behaves in Jammu and Kashmir and how it behaves in the Gujarat or in West Bengal or in Orissa, in Rourkela, they are not always same, because in a very low temperature case, how a battery will like its life cycle will be, and in high temperature case also, they are extremely two conditions, whereas the battery wants a particular in the middle range. So that is also factor which affects the battery life. And as the battery life is affected, of course, the capacity to be chosen is also would also be affected. And the charging schedule, whether you are charging in, as I said, that if you have refilling option, then the lower capacity thing also will suffice your purpose, a half-liter water bottle or even 200 ml water bottle. But if you don't have that option, then that's a different issue. So in some cases, we charge in the middle. In some cases, when we come back home in the evening from office, we will charge probably overnight. So charging schedule is another factor which affects it. And power management strategy, as I said, if multiple devices are used, one battery and one fuel cell, for example, how much we are taking from battery, how much from fuel cell, and how this power division or like management is happening, that will affect. So here what I said that I will discuss first, instead of generalizing the thing, I will take one simple case and I will show you that how the sizing is done, and rather how we have done. Of course, there are other ways also. And then the second, in first case, we will take like a e-rickshaw, and then second, we will take one city bus, and then if time permits, we will go for this machine learning thing. The first problem is to optimally size and analyze the economic benefits. Like, so why we are going for optimal sizing? I said there are multiple advantages, and one option was to reduce the cost also, right? So here we will see that, okay, if changing the topology or optimally sizing is giving me any benefit. So that we will see on a particular case, which is rickshaw. Now, so how to start with? Now, first we need to know the system. So how the powertrain configuration, as I said, that powertrain also affects or impacts the sizing, then driving cycle, like in which route. So definitely, if you are from your home, you are going to just bank for 30 minutes, then the kind of food or other things you will take with you, and you are going for a whole day journey, you are going for a 3 days travel. Of course, in different cases, you will take different things along with you, right? So same thing, we should first know that in on an average, my vehicle will run in which route. Some of us who stay inside our campus, probably only the inside campus our vehicle runs. So if we select some, or maybe in once in a month we go to town, or we go for a long journey in 3 months time, or so, should we consider that one day thing, or shall we consider what we're doing normally? So in this case, definitely our thing would be on an average which route we are taking. That is the driving route, and that is called driving cycle also. And what we are going to decide now, our objective is to optimally decide that how many cells are to be connected and in which fashion to be connected. So of course we need to know or we need to capture the behavior or the property of that particular cell or device. So that's why we are not, when we are sizing, we are not using the actual battery or the actual supercapacitor or actual fuel cell, we will use the model. So the model is also important factor. If you wrongly model while doing the optimal sizing, of course, actual requirement is different, or actual behavior of the your energy storage device is different, and what you have sized based on something else, when you will use it practically, it will not provide you the same performance. So it is very important to consider the ESD or energy storage device or ESS, which so here I'll be sometimes I'll be using ESS and ESD. Just consider that both at this moment we are considering the same. So model of energy storage device is also to be taken care or to be included when we are going for sizing. And the third thing, so where already we have got to know that how the drivetrain or the powertrain is connected. So how many converters are there, what are the various energy storage devices, how they are connected, what kind of motor is connected, so efficiency of those motors, many other things. I mean, whatever is gearbox, then like as I said, vehicle dynamics, that even I mean each of the thing, what kind of tire is in your vehicle, everything is involved here. And the route, whether it's a steep route or it's a plane or where you are, everything will decide that what kind of or what is the capacity of your energy storage device which will fulfill your purpose. Then once all this modeling and everything are known to us, and then we will also look if we have only one storage device, one type of storage device or multiple types of storage device. In that case, we also need to take care of the power management strategy which we are using. We will see what we do. And then once everything is done, now we need to find like go for the optimal sizing. And for that, what we know, in general, we know for any optimization problem, we need to have one objective function and then some constants. So objective function is either to minimize or to maximize, minimization of the cost and maximization of the profit. And then the constants to be fulfilled, constants can be of two types: equality constants, inequality constants. And then we need also to decide that what kind of optimization algorithm we will be applying in this. In this study, what we have done, we have mostly applied PSO, which is a standard thing. The whole lot of techniques are there, algorithms are there. Many researchers are only focusing on that part, but I will exclude that discussion in this case. And then this optimal sizing would be done. So these are the things I require, and then this formulation of the problem would be done, and using this algorithm I will get my optimal sizes. That means number of series cells and number of parallel, so those branches to be connected. And then final thing, as I said, why we are going for optimal sizing, one thing is also to basically reduce the cost or to, so we will check whether that, yeah. So in this particular case, we have, so this is the simplistic presentation. We have energy storage system or energy storage device. As I said, it can be a single one, the only battery, for example, or fuel cell, or it can be combination of battery, supercapacitor, fuel cell. And then there are motor controller and then motor, and then you have these wheels, and through gearbox, this is connected. And I said that various topologies possible. And again, this topology and other things are not our interest in this discussion. Other speakers have already spoken about these things, and then in future also others, some speakers will talk about it. But which we have considered here is two cases. In one case, we have considered single ESS, and in another case, we have considered combination of two ESS. So three types of energy storage system we have considered here. One is lead acid battery, one is lithium ion battery, and the third one is supercapacitor. SC is supercapacitor. Now, also we have used the combination of lead acid and lithium ion, then lead acid and supercapacitor, and lithium ion and supercapacitor. Lead acid supercapacitor, lithium ion supercapacitor we have used. So in this way, total 8 cases we have considered. When we are, so in case of lead acid and lithium ion, we have gone for passive, that means without converter. We have gone for active. You can see that in case of lead acid, we have not gone single lead acid with the active. And anyway, so you can see these are the combinations, semi-active and fully active. In case of semi-active, the supercapacitor is only connected with the converter, battery is directly connected to the DC bus. So what kind of route we have considered? We have taken a very small route. It's 2 points A and B. It's only 5 minutes journey. Then in that 5 minutes, it is moving from A to B, and another 5 minutes B to A. This is a total trip. Completing one trip, it is waiting for 5 minutes. So you can see here one trip only having 1.55 kilometer. I mean, so 1.5 kilometer only. In this way, we are actually considering from morning 8 a.m. to 6 p.m. This 10 hours, this trip would be, so in 1 hour time, 3 trips. In that way, total 30 trips. And one trip I mean A to B and B to A. This has been recorded using a smartphone-based GPS. So what are the steps involved in optimal sizing of PSS? Let's see the time. These are the steps involved in optimal sizing of PSS in electric vehicles. So I have already said it. So just to summarize, first we need to know what kind of vehicle and in which route and what kind of ESS we are using. And then based on this route and based on the type of vehicle or vehicle dynamics, we need to calculate that how much amount of power is required to run the vehicle. That means power required at the wheel. And then power required at the wheel to be converted to the power required in the DC bus. Of course, then we will consider all the efficiencies of all those components which are connected in between this wheel and this DC bus. And then if the DC bus and the battery or energy storage devices are again connected with some converters, then that will also be considered. And if there are multiple storage devices, then that energy management strategies, that how the power split is happening, that also has to be involved. And finally, using one particular optimization algorithm with the formulation of the problem. And here the formulation of problem means that finding out the objective function, inequality constants, equality constants, and then we'll run the this optimization algorithm and we will find this thing. So we'll, as I said, for this particular case, we will see one by one. So first is how to calculate the demand power to run the vehicle. So the four kinds of forces are, or you can say the power involved. This PG, this is, you can call that this is coming from the grading force or grading resistance, which is due to the gravitational thing. Then this is the rolling like power due to the rolling force and to overcome the rolling force rather. And then this is the aerodynamic one. So to overcome the aerodynamic drag, which will be faced by the vehicle when it is moving. So to overcome that force, this P arrow, and to run the vehicle, this the acceleration due to the to accelerate the vehicle, this is the PACC. So gravitational force, aerodynamic force, rolling force, and acceleration force. So for these things, we need total power, which we are calling as the demand by the vehicle to run the vehicle. So any standard book and a paper, we can find this equation. Now, if we see here, when we are writing this P demand, along with this, we have also incorporated P aux, which are not kind of like, we haven't talked here. What is this P auxiliary? Now, to suppose some vehicle may have air conditioning system, some vehicle may not have, some vehicle may have high musical system like high quality music system, then like the door opening and closing, the automatic, more automation is there, more power, auxiliary power requirement will be there. So that's why that has been kept a separate thing. In our study, we in some cases we have considered a particular amount of auxiliary power, and so depending on the application, this auxiliary power can be decided. Other things, so this M is the mass, mdvdt, this is giving us the this acceleration force, and then multiplied with v is giving the power. So you can see this is due to the acceleration, and mg sine theta is gravitational, mu mg cos theta, this is the rolling one, and this half CD rho A frontal. A frontal is the frontal area which is facing the aerodynamic drag of the vehicle. This is the air density, and this is the drag coefficient, and this V is the vehicle velocity, and VW is the wind velocity. Um, this is the which is acting actually in opposition. So in that way, we will take the value. And overall, this is the power demand in the wheel to run the vehicle in a particular speed, that is the V here. So first thing is to calculate that one. As I said here, calculation of power required to run the vehicle. And then we will calculate the power demand on DC bus, which would be supplied by the energy storage device. So how to calculate this one? Now, by incorporating the efficiency, I mean, all the losses involved in the components in between the wheel and the DC bus or the energy storage here in this DC bus, we will convert this P demand to the P required at that point or DC bus, which would be supplied by the energy storage system. Now, we said that our main focus is the energy storage device. So we need to incorporate that. And how we incorporate that? It's not the physical storage device we will incorporate. It is its model we will incorporate. So in our case, as we said, the three types of energy storage devices we are using. One is lithium-ion battery, one is supercapacitor, and a third one is lead-acid battery. So we have modeled them. Now, there are multiple ways of modeling. Again, a group of researchers are totally focusing on the modeling. And so when we were focusing on the energy storage sizing, we are not here to discuss the modeling part, but we would only say that, okay, this is the model we have used. Now, this model is called equivalent circuit model. So there is another category called electrochemical model, which is very accurate but complex also. It's not so easy to find out the parameters of those models. But equivalent circuit model is a trade-off between the accuracy and the complexity. So most of the time in application, application engineers go for this equivalent circuit model. Now, again, equivalent circuit models, in this case, we have used open circuit voltage based, and two parallel RC are involved. So this is called 2RC model, OCB with 2RC model, and this is the equivalent series resistance. But the simplest model is having only this OCV and this ESR. And then the second possibility is this ESR having only one branch of RC, one pair of RC, and then OCV. And here we have taken 2RC branch. Someone can go for the 3 also. Yes, if we increase the number of such branches, it would increase the accuracy, but there is a limit. If we go on increasing this RC branches, it's not necessarily, it will increase the accuracy is very less compared to the complexity involved. So it's your application. You have to decide whether you are going to go for a simple model or the complicated model. And same thing here, lead-acid battery has been modeled. Again, this is the equivalent circuit model. And this is the supercapacitor. In this case, you can see in supercapacitor, the OCB thing is not there, but there are many equivalent circuit models where OCB is also involved. So without OCB, it can be modeled. Considering OCB also, it can be modeled. Here we have used these 3 models, and our focus is not in the modeling. So once we know our, we have already decided our route, that total day, this 30 trips, of each trips of 1.55 kilometer, and total travel time is this from 8 a.m. to 6 p.m. So now we know the route. We know the vehicle, like which formula to be used. We know it's e-rickshaw, and now we also know the energy storage devices. Depending on our 8 topologies, if we remember that there we considered that this storage device, this kind of passive, active, semi-active, fully active combinations, all those things, considering now we have got everything. Now we have to look at the power management strategy. Now, when we have only, the single ESS, only battery or only supercapacitor, only either lead acid or lithium-ion battery, then there is no management strategy required because it's only one thing. So whole power has to come from that one. So that is what mean running a single ESS, whole demand power to be supplied by the connected energy storage device. But when it is HESS, that is the hybrid energy storage system, we can intelligently actually decide that how much and when to come from battery and how much and when to come from supercapacitor. So basically, because the battery has comparatively low power density compared to the supercapacitor, so it usually used to supply the average power, not the spikes or the peaks. And so it will supply the average power. In our case, we decided in that way, but there are intelligent way of deciding. And then PSC module or the supercapacitor module will supply total demand power minus whatever the battery has supplied. Now, in this case, we have considered the very simple rule, but this rule-based strategy can also be made better, considering check the SOC of the battery. So it's not that always the average power to be supplied by the battery. If battery SOC high compared to the supercapacitor, then take more power from battery. So rule can also be made simple, or rule can be, there can be 30 rules for a particular strategy, and there can be only 3-4 rules for this case. So of course, when the rules are more, your strategy would be better. In this case, the simple thing we took, the average power, battery, rest of the thing, supercapacitor. Waiting time, here one thing, because the supercapacitor life cycle, that means that how many times it can be charged and discharged, it's in lakhs or ideally infinite. So if you charge discharge multiple times, it doesn't matter. But in case of battery, the cycle life maybe 1200, in some cases 600, 3000, it is limited. No more than 10,000, for example. So in that case, if you charge discharge multiple times, then in a few days only you need to replace the battery. So in that case, here we decided that in that 5 minutes waiting period in between two trips, only the supercapacitor will be charged. So here our assumption is the 2 points we have considered, A and B, in one side actually there is a charging facility. Okay, so am I connected? Just to check.
Yes, ma'am.
Okay, okay. Just let me switch off this notification thing. Yeah. So that's all about what we have. Now the problem formulation. So as we said, the first thing is to find out the objective function. In this case, objective function is minimization of the cost. So what are the costs involved? The cost of the energy storage device and cost of the converter, if any. So in case of semi-active or fully active topology, the converter costs are also involved. I mean, the extra converters would be there. That AC, DC to AC converters are, of course, it is always there. But other than that, also extra converter, depending on this, whether the storage device is directly connected to the DC bus or not, all those things are involved. So to the cost of the energy storage device and cost of the converters, if it is there. Now, what are the things we want to find out? We said the sizing means finding out the capacity, how the capacity is decided, that how many cells are connected, and how usually the cells are connected in combination of the series and parallel. So this NSB and NP, or NS basically telling how many series cells, and NP telling how many such branches parallel to be connected in parallel. Now the P stands for battery, whether it's lithium-ion battery or lead-acid battery, and SC stands for supercapacitor. So in three cases, in all these cases, our objective is to find out the number of series cells, number of parallel cell or parallel branches, and then what is the rating of the converter, that also where the converter is involved, and what we will supply to this algorithm, that number one, our root, that, and that means the root and the model of energy storage device and everything that that power demand what we calculated based on the gravitational force, rolling force, aerodynamic force, auxiliary power, and acceleration, that we will tell ki, see, this you have to supply. Then along with that, so here let me just, so cost of lithium, in case of lithium-ion battery, it is the cost of one cell into the number of series cell in a branch and number of parallel branches. Same thing in case of lead-acid battery and supercapacitor also. And the converter cost is basically C converter, that, and this C converter is what? The cost of this DC converter with respect to P-con. That means per watt, how much is the cost? And then P-con is the how much is the power rating. So C-con and P-con is giving me the total power. Okay. So we said that two types of constants are there, equality constants and inequality constant. Here equality constant is the power demand to be fulfilled. Because I want to run my vehicle and that requires this amount of power at the wheel. So why this? Oh, okay. So this PM, it is the motor power actually. Now motor power is coming from what? Now demand power and divided by the efficiency, which is of course lesser than 1. So it is more than what is at the wheel demand. And here eta con is the efficiency of the converters, and alpha, basically it is 1 in case of when it is active, and otherwise it is 0. Okay, now inequality constants, SOC, state of charge, it is whether it's single ESS or HESS. In all the cases we need to check that because there has to be, we said that when we need to fulfill the drivability requirement, we also need to think about the safety of the energy storage device. So if my state of charge goes below certain thing and above certain thing, of course the safety purpose like that would be hampered. So that's why there is a lower and upper limit of the state of charge. Similarly, power also. So manufacturer provides some data sheet where they say ki, this is the safe operating range. You should not go beyond this. Now, in case of converter also, we will have the minimum and maximum of the duty ratio. And then all these things are some constants. So with these constants, with this drive cycle, with the vehicle information, all these with these 8 topologies, we perform this optimal sizing thing using the PSO algorithm, particle swarm optimization. As I said, you can use any other thing, maybe some other can give even better accuracy, but we found that this is good. So you can see these are NSP means, that means 4 cell to be connected in series, and such branches, 25 such branches to be connected. So total is 4 into 25. And in case of second, it's 1227. So many combinations. Now here one thing is, we should not say ki here 1227 and 750. Of course, these are two different things. because if you check, the case 1 is lead acid battery and case 2 is lithium ion battery, and the unit cell what we have decided, that is providing this 425 12 27. It's not that each cell, the lithium ion cell or supercapacitor cell, one lead acid battery cell, they are having the same capacity. We have decided based on the availability, commercial cells available, we have decided, and specifically in case of lead acid battery, we have decided what is conventionally used. And from there, we have found this one. I should have the specification, but I'm not getting it. Maybe it would be somewhere. I'll check. So ultimately, if you see this, these are the numbers, but if you look at the voltage and ampere hour rating, so we have found out this one. Now you can see in case of case 1, 100 ampere hour is the capacity, but in case of case 2, 69.75 ampere hour has been the capacity. Again, if you look at the other cases, in some cases it is only 40 ampere hour is the capacity. So why this ampere hour capacity has come different? Now, depending on many other factors. First of all, the minimum cell which we have used, and as we said that if the unit cell is of high value, then connecting only one extra cell or one extra branch will increase its ampere hour. So in that way, it's not always that different type of storage devices will have the unit cell capacity same, and because they are not same, our ultimate result may not be same. Okay, so now we said, so you can see from this table, we have come up with DC-DC converter ratings also, where actually, so this first two case was fully passive. This one's first 1 and 2. In third case, it was third and fourth was active. So because third and fourth was active, one was with lithium-ion battery, one was with supercapacitor. So the with battery and with supercapacitor, in both the cases, the converter rating is 1021 watt. And then here it's fully active. So with battery also we have converter, with supercapacitor also we have converters, and these are semi-active. So that's why only the supercapacitor has the converters, but the battery is directly connected with the DC bus. Now with all these findings, we have found, if we find out the cost, now here I should make some comment that this calculation we did like a few years back. So maybe today if you do the calculation will be different. Because the sale cost has changed, converter cost may have changed, but considering that time, what we found that the least cost is coming, and these costs are calculated considering the 5 years. It's not the initial cost. When we're talking about the 5 years, let me go here.
Excuse me, ma'am. Sorry to disturb.
Yeah.
Ma'am,
Please.
here we need to consider both, I mean, battery and supercapacitor, but case 4 is only capacitors. Because while capacitors,
what we used both battery
both
and
battery
supercapacitor.
for the average power
Sorry
and
to
also
interrupt, but
supercapacitor.
now the session is not open for discussion. Let ma'am complete first, then you will put forward your queries.
Okay, ma'am.
Okay, I will take it down. You just I will try to finish soon so that we can take this question. Okay. So I will come back here, when we come to that session. So here, you can see, I will, as I said, that I will not go into many things if time doesn't permit, but I want to show you that what we did. So let me go to, it's not moving. Yeah. So see how the calculation is done. So this is for a 10 years calculation and case 7. Where basically lead acid battery and supercapacitor both are there, and both are connected with the converters, because the case 7 was fully active. I guess so. Yeah, lead acid plus supercapacitor with fully active. Now, what are the various costs we have considered? Cost of battery module, which is the initial cost plus replacement cost plus number of replacement. In 10 years time, we need to think of how many times we have to replace it. Now, when we are considering the replacement cost, we are also considering that the second-hand battery, if that person sells, then or it's a buyback offer that you give your second-hand battery to us, we will give you in the reduced cost. Everything has been considered. You see, the new battery, a lead-acid battery of 13,600. When we have considered the replacement cost, we have considered 10,000 because we actually talked to the vendor. So then we came to know that basically later on they give it back, and so they get it in the reduced cost of 10,000. And we found that they usually change it in the 6 months time. So in that way, we considered 19 times they have to replace. And so this was the total cost. This was the total cost of what? Total cost of the battery module. The cost of energy consumption we have also considered because the battery has to charge from grid. Super capacitor is charging from grid. In this case, we are considering the battery charging is taking how much price. So as I said, that this INR per kilowatt hour into days, into years, everything has been considered, and we found this is the case. Now, this cost will come down if we are considering a charging station where the solar-based charging station is used. Similarly, DC-DC converter cost has been cost per watt into power rating. So, in this fully active case, if you remember, it was 370 watt only in case of battery. So 17 into 370. But in case of supercapacitor module, the converter was of 781, and the cost in this case, here it's cost of supercapacitor, it's not the converter. Number of total cell into cost per cell, that has been considered. Same thing is for cost of energy. Now here you can see battery module, we considered initial cost, replacement cost, and 19 times replacement. But in case of supercapacitor, it's only the one time. There is no replacement cost because I said supercapacitor ideally has lakhs of life cycle. That means number of charge and discharge, how many times you can do. So in 10 years time, although every day in this many times we are charging and discharging, but if we believe manufacturer, in that case, there is no need to replace the supercapacitor cell. And that's why there is no replacement cost, only the initial cost. But we have also considered the energy consumption by the supercapacitor for charging, and the converter cost also being considered. And so totally, here the converter rating was 651 and 17 rupee per watt. So considering that, this is the total cost. I don't know if the question was related to this, then it may be clear. Otherwise, I will come to this later. Okay, so we have taken up this or we have analyzed this for 5 years and the 10 years, and what we have found? We found that active topology based supercapacitor configuration, we found it to be cost effective for both 5 and 10 years of vehicle life. But there was one assumption in the beginning. I said that we are assuming that after each trip, there is a 5 minutes waiting time, and in that waiting time, supercapacitor will be charged. So there is a charging facility available. We found that optimal sizing reduced the cost because if you see that, yes, the 5 years time, the conventional e-rickshaw is basically taking 2,63,000, where we are with this one, we're getting 126. Again, I'm saying that, of course, if we go for the lithium-ion battery instead of this lead acid, then actually it is coming to be 139. So all these costs are being calculated based on the data available in the various sources, and that is in a few years back. Today it may change. So in that case, don't think that it's probably we are representing a wrong thing. So that difference may be due to this one only. Okay. So now I'll just because I have, I guess, only 10 minutes, 5-10 minutes time to conclude. I'll not go much detail. So here the question is, when we have considered, for example, in that 5 minutes drive cycle also, what we are considering, every day every trip will be of 5 minutes. It can go in 5 minutes, it can come back in 5 minutes, it will wait in 5 minutes. But is it possible? No. Sometime due to, okay, we have taken a very ideal case within a campus, this is. But if you think in a city, you are traveling, I don't know where you are, suppose Rourkela. So from the inside the campus to the Rourkela city, it's not that every day your vehicle will reach there in the same time. Someday it takes 15 minutes time, it may take 18 minutes time, it can take 10 minutes time, it can even take 25 minutes time. If heavy traffic is there, it is totally different. So when we have found out this optimal sizing, that means this many cells to be series, parallel, this is the capacity, this is the cost, considering all these things ideal. But in practice, many things differ. Even today, you are driving the car, tomorrow someone else drive the car, same route, everything same, then also the time will be different. And it makes a huge difference because you remember there is auxiliary power is also involved. So if your run time, one day is 25 minutes, another day is 35 minutes, in 10 minutes, your auxiliary power is being consumed. Many such trips you are doing, so that will change your energy consumption in a day. That will demand different power, and that will demand different energy storage device capacity. So when we are talking about the energy storage device capacity, optimally finding out the sizing, but considering the standard drive cycle, that my route is fixed and this is the power demand in that route, then basically we are living in an ideal world, not in the practical, because many things change. So the second study we did is how in driving cycle uncertainty, that means you're in the same route also, different drivers, different day, different traffic condition, many other things can change, and then even weather condition will change. In that case, this drives the sizing what we did, will that serve the purpose? We found no. So the same framework we used, that powertrain configuration. As I said, that this study we did for a city bus, not the e-rickshaw running in our campus. So everything we did in the previous case, it's the same, only the vehicle dynamics now different, drive cycle different. We have used a different set of models. So what is the assumption here? We have considered a city bus, which total distance covered in a day is 240 kilometer. And how this 240 kilometer is covered? Now 1 kilometer is one trip is 12 kilometers. Such 20 trips are being done, and with a gap of 1330 seconds. Or 22 minutes after each trip. Previously, we considered 5 minutes, and each trip was of 1.5 kilometer. Here, each trip is of 12 kilometer. So here also we have considered supercapacitor, only battery, and combination of battery and supercapacitor. So only difference is now we are generating some test drive cycles. Now, how these test drive cycles are generated? There are many ways to generate test drive cycles by combining or incorporating the uncertainties. We have incorporated the uncertainties using the micro trip and micro ideal. So this is the bus configuration. I will not go into that. Okay, so we have considered this 12 kilometer, this travel thing, it is called urban dynamometer driving schedule, UDDS, very standard thing. And that test drive cycle. So standard drive cycle means ideal, one particular day can happen that, but test drive cycle means different day, different thing can happen. And how different thing can happen? Because today in one particular traffic signal, you have stopped for 1 minute, and another day you may not stop there, and other day you may find that you had to wait for 3 minutes. So total this 12 kilometers, someday it may take this minutes time, someday it may take extra 10 minutes time. So this is called micro tip, micro ideal approach. I don't have time to discuss actually, so I will skip it. So in that way, we have generated 4,000 such drive cycles, test drive cycles. That means as if we are traveling the same route 4,000 days. Same thing, all the modeling done. These are the battery and supercapacitor cell specifications. And same thing, optimal sizing, set of input variables. What we are providing? We're providing the battery model, we are providing the route, we are providing the vehicle dynamics, all the information. Then the objective function is the minimization of the cost, then equality constant, inequality constant. So the demand power, per cell cost to be provided, per kilowatt cost of the DC-DC converter to be provided. And the objective function, already we said, number of battery cell in series, number of parallel branches into battery cell cost. Same thing in for supercapacitor also. And in case of HESS, these are the summation of these two things. And when the battery or SCLN configuration, again, in previous case, we did not consider the regenerative action. That means during the braking, the battery is getting charged from the vehicle actually due to the braking action. But in city bus, we considered that also. So during motoring action, the battery would be, or battery or AC power would be this, and during regenerative action, it would be different. Same thing in case of HESS also. The same set of inequality constants, charge, voltage, power, current, all these things. Again, if boost, it works in the boost mode and buck mode. Why it is coming to the boost and buck here? Because the regenerative time, it would be buck, and it is motoring time, it would be boost. So considering the standard UDTS, we have found this is the sizing. That means 66 number of cells in a series branch, and such 2701 branches are to be connected in parallel. And HESS, this is the combination. Sorry, in SC, this is the combination, and HESS, these are the combinations. So these are basically to show you that yes, all the constraints are being satisfied. In all the cases, power demand is also being satisfied, combining both the in case of battery and supercapacitor combination case. So see, the average power has been supplied by battery. I'll skip this one. Okay, so what we start, so we took up one thing to see that if the uncertainty, we put uncertainty in everything. We did it in like in every traffic signal, how much time it is spending, and like speed also. So in each moment, the speed uncertainty also. Today, I have crossed one position with a suppose 30 km/h speed, and we are putting uncertainty of 10%, 2.5% to 10% next day. In that way, we have generated 4,000 cycles. And then we found the worst case scenario, what we saw, that even in 2.5% in this range of uncertainty, battery capacity has to be changed approximately 16%. So initially, suppose your battery capacity came to be 100 ampere hour in a in considering the ideal standard drive cycle UDTS, but if the uncertainty will always be there, and the worst case scenario, you may need to have 116 ampere hour capacity if you want to satisfy everything. Similarly, in case of supercapacitor, your due to uncertainty, the requirement is more, 25%. So that we did, and we did some experiment also, and we found that yeah, all these things are thing. So basically, to summarize, the change in ESS size. So uncertainty and the sizing change are not linear, but of course it demands that. A small uncertainty can lead to a high change requirement in the change in the ESS size, because the total duration spent in one trip may be totally different due to the traffic signal, and that can significantly affect the power requirement, and that can basically demand different ESS size. And we found that battery alone combination in such a case can handle better uncertainty. But yes, here we have a confession, or that the way we generated the test drive cycle using the micro trip and micro ideal, which I could not discuss due to the time limit. There are other ways also. And later on, we found that we could generate the TDC in a better way, putting some extra limits so that the worst case scenario we would not have exceeded. So maybe that can also be considered in future, that which one is the best approach to generate the test drive cycle, to check that how the ESS gets affected by the uncertainty involved in practice. Okay, so my third thing, what I will not discuss now, but I would just say, see, in this case, we have used the PSO approach algorithm. But if you have already, we have 4,000 such test drive cycles and corresponding 4,000 sizes of the cells, or battery module, supercapacitor module combination. Now, with this database, if we now apply the machine learning algorithm, what we generated in this case, in PSO, we just, I will show you the results. Yeah. So we compared it that if you use machine learning, what is required here in 10 to 12 hours time per drive cycle, machine learning can generate the same result in 10 minutes time. Same thing, I mean, kind of hour and minute conversion, which here could generate in 1 hour time. It is giving the same result in 1 minute time. In 14 to 16 hours, what result we are getting using the conventional optimization approach, machine learning can give 12 to 13 minutes the same result. So maybe some of you can think of it. So with this, I will stop here. So what we basically here I discussed, first thing is why sizing important, and what are the basic steps involved in sizing. And we took up one case study of e-rickshaw. We did it in sizing, and then we also did the cost analysis, and we found in 5 and 10 years case, supercapacitor alone with the active topology was the best, like the minimum cost option. But here our assumption was that charging station is there. Of course, that charging option was not there. Lithium-ion battery was the best option. And then we also little bit went through, I mean, of course, in rush, that in practice, that particular trip will not have the same drive cycle every day, although the route is same, due to many reasons, including traffic, weather conditions, the drivers, vehicle status. So the same energy storage device may not fulfill every day's demand. So we need to think the worst case scenario also. So we can make a trade-off that, okay, this limit we will put and we will go for a little bit higher energy storage device capacity. And then I said in case of this, the time consumption, the time requirement is more if we go for the conventional optimization approach. Rather, we can go for the machine learning one. Once we have the database, in that case, with the low time, very less time, we can do it. So some of you can work if you want, and in this thing, as I said, that the TDC generation, what we did in MI and micro ideal and micro trip approach, you can go into the different approach, and then you can see the effect. And then also like unit cell, what we are selecting, that one particular cell, the base unit or the unit cell, in case of supercapacitor or lithium-ion battery or lead-acid battery, if we change that, then what impact would be? We have also done some study, but I'm not presenting here. And then, of course, cell balancing is an important thing. If cell balancing is done, cell balancing not done, then how the sizing would be impacted and all. So, with this, I will conclude my presentation.
Now the session is open for discussion. So I request audience to put forward the questions. Ma'am.
I can't hear. One voice is coming, but it's not clear.
First thing. మన దగ్గర ఇంతవరకు ఆయన తెలుసు బట్ నాట్ క్లారిటీగా తెలియదు పాత ఇన్ఫర్మేషన్ ఆయన దగ్గర లేదు.
Your voice is not clear.
Actually, he is not
There might
asking
be some
question.
internet issue. Your voice is not clear. We are not getting the question.
No, he is actually not asking the question. His mic is on.
Oh, okay. You can mute. You can mute. The organizer
Ma'am,
can mute.
I have a question, ma'am.
Yeah, sure.
During that force analysis, you have taken that mg sin theta. That means, have you assumed that vehicle is in inclined shape, or if it is in horizontal position, it will be fine?
Yeah. Thank you for. Yeah, it's a good question. Yeah, I forgot to mention that. So can someone mute that person who is not talking but mic is on and the background
Mr.
noise is
Bhara
there?
Prasad, can you please switch off your mic?
Okay.
Mr. Bhara Prasad.
అలాగే అంటే అసలు నన్ను కారణం చేస్తారు ఎందుకంటే వీటి గురించి
Fine. We may ignore him. So here my answer is yes. We are considering that is the basically angle or road angle. But in our study, we have assumed it to be 0. So this is a very ideal case we have considered. But this theta is basically if there is an inclination, road inclination angle. You are right. So that can also be studied. And here the result, so we found there is a little difference in the practical result and the simulation one. And that was another reason because our campus is not so flat. But in simulation, we considered it is flat. But when it was in practice, there was inclination. So there was a difference.
And ma'am, that you know that if your battery is getting completely charged or if it is discharged, then its weight, there is a difference in weight of the battery.
Yeah.
So have you considered that factor while designing or sizing the battery?
We have considered in one case, city bus case, we have taken the passengers weight, other whatever the like when it is increasing. But in case of e-rickshaw, we have not considered those weights. But yes, that's a very valid question, and that's an important factor because ESS, even the passengers weight will make a huge difference in ESS size. We have found like 10% difference is coming because of the. So we should actually consider when I'm writing here that M total is the all the masses we are considering, and it is actually changing. But yes, we could not, I would say it was not very practical, but yes, we have considered.
Okay, ma'am, another aspect is that battery temperature, because you know that some incidents are happening that battery is getting burnt because I think the rise in temperature. So no point I have seen that battery temperature you have considered. Have you ignored it?
Yes. Yeah. So here it's not shown. The model, I probably earlier said the temperature and aging both have. So in one case, so when we have the model I showed you, that equivalent circuit model, that was only the electrical one. But later on, we have incorporated the, 1 minute. Yeah. For example, in this case, it is only the electrical model, but later on we have incorporated the aging and temperature model also. I don't have that result here, the study. So when we have that replacement, we have considered for especially for the lithium-ion battery, we have had some assumption that our vehicle is running in such kind of temperature, and in each day it is basically charging from this. So its depth of discharge is to be 30%, and it's up to 90%. We have considered, suppose 30 to 90. Then if each day it moves from, charges 30 to 90, then how many life cycle, like, so each day what is the capacity decrease is happening. So we have incorporated that in some study, not the first case.
Okay, thank you, ma'am. Thank you for.
Thank you for asking these questions, because these are the very important aspects which I did not mention, but I should have.
Good morning, ma'am.
Yeah, good morning.
Ma'am, can we design the vehicle supercapacitor alone, or compulsory we need to combination of battery?
No, it's not compulsory, because so far I know the China first bus was only supercapacitor based. So they have in each stoppage. So whenever you have more stoppages, then SC based bus is better than rather battery based, because I said that supercapacitor can be charged and discharged ideally in finite time. But in case of battery, if you charge discharge multiple times in a day, its life cycle will be reduced. So if you have such facility where also I mentioned one point, that regenerative braking. So suppose your route is such that many times the braking is there. So then what is happening? Specifically, if you think there is an inclined road, you are coming from the hilltop to the ground down, then most of the time your brake will be applied, and with that brake only your whatever the storage devices you are using, it would be charged. And I know there is one case, at least I don't remember where it is. They are calling it zero cost vehicle, because when they are coming in the morning to the office from hilltop to the city, for example, their batteries, I mean, they are using supercapacitor also, it is getting charged, and with that charge only they are going back in the evening when they are like out of office. So in such cases, and specifically this is a special case, but in most of the cases in city, if you have multiple charging options, charging stations, and specifically regenerative braking can happen, then supercapacitor alone is a good combination. But yes, if there is no charging facility, long run journey, then you must have the battery.
Okay, ma'am. One more thing. Supercapacitor gives the transients power, and battery gives the average power. How it will practically it will be? I didn't get him, ma'am.
Okay.
How it will utilize?
Yeah, so there is a energy management strategy. I think another speaker will discuss, probably. If they have not discussed, they will discuss. So for my knowledge, that some of the speakers will talk about the energy management, combining this battery or fuel cell or battery supercapacitor and solar. So that management strategy itself, so there will be an algorithm which will have, so there is one assumption that you have prior information of the next moment what power demand is coming. So when you know the next moment power demand, immediately this algorithm is deciding that what is so there is a filter option, for example. So it will filter out that in this demand, which one is the average one and which one is of high frequency demand. So low frequency and high frequency filtering, this is one option I am seeing. There are multiple ways. So this filter will decide that this is the high frequency component. So supercapacitor will supply, and this is the low frequency power requirement. So that would be supplied by the battery. So one approach I will see, you can check that filtering approach for power management, energy management in hybrid energy storage device. But other optimal control can be applied. We have used the what it's called, forgetting the name. So we have also used that, and it's working. Practically we have done.
So it means it's starting acceleration. We can use supercapacitor. Runtime we can use the battery.
No, it's not that this time battery, this time together, one portion of the power requirement is coming from the battery, one portion of the requirement coming from the supercapacitor. So simultaneously can happen.
Okay.
Individual can happen.
Thank you, ma'am.
Okay, thank you so much.
Excuse me, ma'am.
Yeah.
Ma'am, in your case, what is the life cycle of the battery?
Let me now see you. If I can see the audience face, I'll stop. I'm not seeing anyone. why
My
I'm
video
seeing
is
my-
off, madam.
Okay, fine. Yeah. So tell me, what was your question?
What is the life of your battery that you have designed?
Okay. So in this case, in case of lithium-ion cell, it was under some certain conditions. If you follow what the manufacturer is saying, it was 3000 times actually you can charge discharge in case of lithium-ion cell. In case of supercapacitor, it is in lakhs. And in lead-acid battery, actually, we have considered that in 6 months time, it would be, it needs replacement.
And the working SOC range?
30 to 90 in case of lithium-ion cell.
And DOD?
Yeah, 30 is the DOD we have considered. And the manufacturer has also said that if we move in this 30 to 90 range, this cell, so this is the case. If you move beyond this, that means below 30 and above 90, then you suppose this 3000 will come down to 2200. Even if you like, so it's not only the DOD and SOC, also that the charging current and the discharging current. So C rate, if you go with the high C rate, or temperature. So these are many factors which will actually impact. But if you follow the set of safe operating regions, what the manufacturer have said, that this 30 to 90, and then C rate is of, suppose 1C is the maximum one. In some case, actually we go for 4C, 6C, but those will impact. Otherwise, like it will give. I recently I bought some cell where they are giving only 600 the number of cycles.
Okay. And also, as one of the fellow participant, he has mentioned safety issue is there in this case, na electric vehicle. So a lot more research is required in this field.
Yes,
So safety,
yes. So
temperature.
specifically, yes. So you can work on the thermal and aging, especially thermal management. So thermal modeling is a very important part. So if you can combine the coupled electrothermal model, so as the temperature is changing, your electrical parameters are also changing. In one case, we have considered all the parameter values are fixed, only SOC dependent, but they are not only SOC dependent, they are SOC dependent and temperature dependent and age dependent. So if we can like have this database, then we can model it considering all those factors. Safety, of course, will be enhanced. So if you are working, then take up the thermal management, because few months back only government has imposed a lot of constraints on all the manufacturers. They gave some timeline, but the companies have failed. They have again increased the deadline. So thermal management is a very good like topic at this moment.
Thanks, ma'am. That's all from me.
Thank you so much.
Due to time constraint, we have to end the discussion. This discussion here. So I would like to extend heartfelt thanks to Professor Munmun Khanra ma'am for sparing some valuable time from a busy schedule. Thank you very much, ma'am, for such an
Thank you so
informative
much.
lecture conveying idea on various aspects of electric vehicles with respect to sizing of energy storage. Thank you, ma'am.
Thank you so much. Have a nice day.
Thank you, Professor Munmun. Thank you very much.
So now it's time for lunch break. The next session will start at 3:30 p.m. Thank you.